we will start the talk by Paul Bourgade, and he graduated Paris 6 and was BP at here and 10 years ago, and he received the Davidson Prize in probability. And I think today's topic is interesting to many people. He's talking about the random matrices and the zeta functions.
So there are some historical connections between random matrix theory and number theory, and we want to add one player in the picture here, which is branching processes. The difference will be that for some more recent conjectures, who are about 10 to 15 years from now, we can actually prove some things. So let me explain you a little bit what's going on. So this is a section of the Riemann zeta function. On the critical strip, and not very high, just between 1 million and 1 million plus 1. And the blue curve is really the critical line, and this is how the modulus of zeta looks there. So of course, supposedly these curves only vanish on this line. And there is a new set of conjectures which emerged in the past decade, which is about what does this, as a random curve, when this 10 to the 6 is chosen random, how does it look like? And one of the messages will be that it's dictated by some branching processes. So the Riemann zeta function is one of the favorite objects by many of us. It can be written as a Dirichlet sum or an Euler product for the real part of the argument greater than 1. Everything is absolutely convergent. Remarkably, we know from Riemann that there is an analytic continuation to the full complex plane, except at 1. And there is a beautiful symmetry which this analytic continuation satisfies, which is this functional equation involving the gamma function. Now, there are three beautiful conjectures, in my view, about the Riemann zeta function that I want to emphasize today. The first one is a connection which started with Hugh Montgomery in 1973. It's a famous story. He calculated the gaps between the renormalized values of the ordinates of the zeros of the zeta function. So just to simplify, let's assume the Riemann hypothesis in this statement. You write the zeros 1/2 plus or minus I gamma k. The gamma k's tend to be more and more dense when you go high along the critical axis, so you rescale them like omega k. And then these omega k's have typical gaps of order 1. And he has calculated the number of these gaps in some interval, AB, for A and B fixed, when you look at more and more of them, x goes to infinity. And he obtained this formula conjecturally. He could prove a version of it which is weaker. And Dyson recognized here that this is the two-point function of the eigenvalue statistics of Gaussian unitary matrices. And this is something which is still poorly understood. Along the same line, because there is a connection with random matrices, Keating and Snaith proposed a conjecture for a long-standing problem, which is now about the moments of the Riemann zeta function along the critical line. So the problem of the moments has a long history going back to Hardy and Littlewood. They were interested in it as a line of attack for the Lindelof hypothesis. If you want to know the growth, if you know the growth of zeta is subpolynomial along the critical axis, of course it implies a bound on the moments. But remarkably, the reciprocal is true. You only need to bound the moments to prove that it's t to the epsilon for any epsilon to prove the Lindelof hypothesis, but that's an outstanding problem. On the other hand, you can also try to conjecture the exact asymptotics. And the conjecture by Keating and Snaith, after many works before, in specific cases, is that it's a product of two prefactors depending on the power, lambda, and it grows like a log t to the lambda square. this lambda square is a sign of some kind of Gaussianity of the behavior of zeta along the critical axis. And this product of two terms, one of them is actually natural. It's a product over primes, which basically would happen if you only kept into account the statistical independent behavior of the primes in the Euler product, for example. And the other one is more mysterious, and that's what they conjectured based on the random matrix analogy, because you can calculate such analogous moments for random unitary matrices based on the formula due to Selberg. And it's a pretty simple factor, and now that's what people believe is the truth. Okay. A more recent conjecture somehow changes the viewpoint, because now we are going to look at a random point along the critical line. So you pick a tau, which is random, uniform between 0 and capital T. So you're on the critical strip, and you look at the random height. And these people, so Fyodorov is and Keating are mathematical physicists, and Hyry is a analytic number theorist working on computational aspects. They could formulate the following conjecture. I will explain it, and it was actually numerically verified in some sense. So the conjecture is that if you look at you take a window which is at random of length 1, and 1 is actually a natural number here. It's kind of the canonical case. You take a window of size order 1 around a random point tau, and you look at the maximum of zeta there, then there is an extremely precise conjecture about how it grows. It's log t divided by double log t to the 3/4, and the 3/4 is a characteristic exponent of some universality class, as we will see. And there is a tail, which is supposedly y exponential minus 2y. What that really means is that if this 1 million becomes random very large, they have a very good estimate on how large the function can be there. Okay. Oh, I will go to that, of course, yes. It's a beautiful chain of ideas, actually. They conjectured it based on many physics heuristics, but these physics heuristics themselves rely ultimately to insights by McKean and Bramson. So it's a strange way, starting in mathematics, going into the physics, and going back to the mathematics. Okay, so other questions so far about the statements? No. So today I really want to emphasize the third one and prove that we can prove not the convergence in distribution, but the upper bound, the right order, and the tail. So the general setting, the universality class that we will place our random matrices or Riemann zeta function into is a so-called log-correlated field. So these are collections of random variables, x indexed by v, and v lives in some metric space, but just think about Rd. And ideally, you would like to define the log-correlated field, meaning that for v and v prime different, the covariance it behaves with a singularity like the log of the distance between the points. It's not quite doable, because then you don't get a bona fide random function. You need to put a cutoff here, and then capital N goes to infinity. Okay, and the question is, why may physicists be interested in this collection of random distributions? There are, in my view, two main reasons. First one would be that this log correlation always appears when you have a superposition of random curves or random waves, such that all scales matter. All wavelengths matter in some sense for the covariance function. So more precisely, there is an example of such a log-correlated field. Imagine you're on the circle, and you take the sum of independent Gaussians divided by square root k times the case mode. Okay. Now, the square root k has been tuned exactly so that all scales matter. Scales being, for example, powers of 10 in the physics way. So if you, because the sum of 1 over k is a harmonic sum, it's clear that that's a good way to tune things with the square root. Now, all scales matter, and if you calculate the covariance, you will get clearly a logarithm function of this type, because if it was a full sum till infinity, you will get the sum of 1 over k exponential minus ik theta minus theta prime, so that's just the log. That's the Taylor expansion of the log. Another reason, which I find quite compelling, is that now if you have such a field and you look at the Gibbs measure it generates, so you just put some weights, exponential minus beta x v, then it has been argued by physicists, in particular Derrida-Spohn, and in much more generality Carpentier-Ledussal, that this is possibly the simplest model exhibiting some replica symmetry breaking, meaning that if you have a correlation which is stronger, it will not happen, and if it's weaker, it will not happen either. What does a replica symmetry breaking? It means that if you sample 2 independent copies along this Gibbs measure, then the overlap will exhibit a transition for some critical temperature. Either it will be completely delocalized in the very high temperature regime, but when beta goes to infinity, on the contrary, at a critical C, it will be either a very substantial overlap or orthogonal, basically, for points which are sampled from this measure. Okay, so the log-correlated fields of interest in this talk, for us, as you can guess, will be first the log of zeta, evaluated at a random, very large height, as a random function. So that's a random function. Okay, and it's easy based on to prove based on some works by Selberg from the 40s that this is log-correlated in the sense that I defined before. And the logarithm of the characteristic polynomial for random matrices is also log-correlated. No, what Selberg did is he calculated the moments of the log of zeta. He got a formula and didn't even care to mention that these are the Gaussian moments. Yeah. So let me now go into more examples, okay, about log-correlated fields. The canonical one is branching Brownian motion. So what happens is you have a standard Brownian motion which starts, and after an exponential clock rings, it splits into 2 parts. And these 2 parts live their own life, and they split again after independent exponential clocks. Okay, so you get a cloud of more and more Brownian trajectories as time goes, because there is more and more branching. How many Brownian motions do you have at time t? Something like an exponential t, because they split more and more. So for a Brownian motion, you are diffusive, but because you have exponential t of them, the maximum is actually ballistic. It follows a line, this red line. And this is in some sense log-correlated if you define the following d, which is not quite a distance, but almost. If you take the log of d, it's t minus this symbol, meaning the generation of the most recent common ancestor. Okay. Then for this d, this is log-correlated, basically. Like the value for one index v and another index v prime, if they have a common ancestor which is very recent, of course they are extremely correlated. Otherwise, they are poorly correlated. And there is a remarkable observation by McKean from 1975 that if you want to understand the FKPP equation for these researchers, it's a classical equation in many domains in physics or even biology and ecology. It has some traveling waves as solutions. There is a probabilistic representation of the solution, just like Feynman-Catch would be a probabilistic representation for second-order parabolic equations and things like this. For example, for step initial condition, the solution would be the probability that the maximum, like this red curve, is smaller than a level x. So because we expect that this is ballistic, this really is a traveling curve then, or a traveling wave. Now, it became of interest to understand this maximum as a consequence. if these points were all independent, you would get a collection of exponential t independent Gaussians. And then it's an exercise for undergraduate students to prove that the maximum would be of order t minus a quarter of log t, okay, based on independence and Taylor expansions. But Bramson proved in 1978 that this is not quite the case, and this is due to the correlations, of course. And it's a t minus a 3/4 of log t. So this, going from 1/4 to 3/4, actually makes a big difference from the physics perspective of Gibbs measures and so on, for example. I want to explain a little bit how Bramson proved this result. Okay? And then we will embed our random matrices and zeta into a setting which is somehow similar. Are there any questions? Okay. So here is what Bramson introduced. Yes? So you give a label to each Brownian motion, and it doesn't quite matter. There is no ordering for them. It just, you give a label no matter what. And V, this symbol, V and V prime, is just the time on which they branched. If you think about a tree, it's the generation of the most recent common ancestor. Yeah, okay, imagine this is V1, V2, V3, and so on. You just give labels to all of the Brownian motions at the end. And this really is the time they branched. Okay. So imagine you want to attack such a problem. Okay, let's try to identify the maximum. If you only deal with expectations, there is no chance it works because it will not take the correlation structure into account. So what you need to do is to maybe do an argument by trying to count the number of high points, this number z, but maybe you want to do that only on a good set which is typical, but which will prevent some inflation in this expectation count. So more precisely, you are looking for an event AV, depending on the label, so that if you look now at the number of labels so that the Brownian motion at the end is greater than what it is expected to be from Bramson's result, but on the event AV, then the expectation will go to 0. But on the other hand, you want the AVs to be typical. That would be enough. Okay? And what Bramson did is that he found a very good AV, which is the following one. He conditions all of these trajectories to be sublinear, to be below this linear barrier, which is just S, basically where the red curve is supposed to be at linear order, plus a large constant. So more precisely, what he does, he says, okay, I am going to trace in green here a curve, deterministic one, and I will prove that with large probability all of my Brownian motions will be below first, and then I will calculate expectation of the number of high points on that event and prove it goes to 0. If you want to implement this, if you think about it, what you really need is to understand the probability of a Brownian motion not to hit a barrier. So basically, the picture would be that you have a barrier here at height m, and the probability that a Brownian motion after some time t ends at a point p and does not hit the upper barrier. When t is very large compared to m and p, it grows like the product of the distances of the endpoints, m times m minus p, divided by t. And it's a very easy calculation for Brownian motion based on the reflection principle. Okay. So because you gain a 1 over t by conditioning on that event, actually it will decrease the naive 1/4 into a 3/4, and it happens to be the truth. There is a matching lower bound. So that was the first example. I explained to you why the first two leading orders in this branching world. Now let's try to see a model for which we could even calculate the distribution of the maximum in a branching or low-correlated setting. So this model is called the Fyodorov-Bouchot model. It's a circular logarithmic random energy model. So what is it? It's pretty simple. You take just a regular polygonal on the circle, and zk's are the vertices. And to each zk or to each k, you will assign a Gaussian with a covariant structure, which is exactly given by the log of the distance. But of course, you need to do something on the diagonal, otherwise it would diverge. So you just put some cutoff. It's the log of capital M, where capital M is a parameter large enough. Okay. And for this model, they have an extremely precise conjecture about what the maximum should be. We do some kind of trivial renormalization, and then the maximum as capital M, which appears here and here, diverges. It should grow like a log m minus a 3/4 again of double log m plus a random variable. And this random variable is supposed to converge in distribution to something with density given by a Bessel function. It's quite remarkable that the maximum in a correlated setting could be conjectured to have a very explicit distribution.
Did you say Bessel function? Is that
Yeah, yeah. It's a modified Bessel function. How did they proceed? So let me try to reproduce the physical reasoning here. So they go through the moments. So they look at the partition function of your field. It's just for your Gibbs weights, the sum of exponential beta vk. And they calculate the moments. Okay. Of course, this is a Gaussian world. Any integral moment, in principle, you can write a formula for it. And what they prove is that when the moment is not too large in terms of the temperature, then there is an explicit formula. And this formula can be obtained thanks to the Selberg integrals again. Okay, so there is a formula. And this formula, something happens when the moment crosses 1 over beta square, obviously because of the gamma factor here. Something needs to happen. And in fact, there is a transition where the moments have a different growth rate when n is large, but no explicit form for this term. Then they say that, okay, we can exhibit a density which will reproduce these moments at least when beta is smaller than 1. Okay, so it's a very good guess. And this ZE is just a renormalization. But the problem is that this is for beta smaller than 1. And obviously, when beta greater than 1, something bad happens. Okay? So there is no way you will recover the maximum from a large temperature estimate. So the miracle is as follows. They say, okay, the beta greater than 1 regime is governed by a freezing scenario, which is that some observables will keep the same expectation as for beta equal 1. And this builds on Derrida, Spohn, and Carpentier-Ledussal. In particular, Derrida and Spohn introduced some observables of this type, which are just Laplace transforms of the partition function itself. And they proved in some settings that it's true that for beta greater than 1, no matter which parameter y you choose, it freezes. This specific observable will freeze. So of course, you can access large beta regime then, and if you have the large beta regime, you will recover the maximum. Now, this freezing scenario, why is this correct? There are some arguments, in particular there is a work of Fyodorov, Ledussal, and Rosso, which says that basically this g beta of y is a function of beta plus 1 over beta. So in particular, if you differentiate just slightly below the critical temperature, the inverse temperature, if it's a function of beta plus 1 over beta, you differentiate, it's always 0, no matter y, which y. So for any single y, this family of observables has a differential equal to 0 at the critical temperature. And that makes them guess that it's actually just flat after. Okay. So that's the physical reasoning. Okay. And now mathematicians have been working, and there are many models for which we understand things in the low-correlated setting, which are highly non-trivial. One of them is the 2D Gaussian free field. So, yes?
So this number, maybe you're about to say this, the number 3/4 has come up in all of these examples. What was special about 3/4?
It's 3/4 itself is not important. What's important, as you say, is that it's the same for all of these models. And it's smaller than 1/4, and it's due to the positive correlations, obviously, of the low-correlated field. And it has a meaning because I think the most compelling explanation may be at the beginning here, that these correlations and the 3/4 that you end up with and so on are a cause for this replica symmetry breaking phenomenon, and it's possibly the simplest model, meaning that if you have stronger correlations or weaker ones, it's not so much the 3/4 changing which will matter. It's more the fact that you will have a critical temperature such that you go from trivial overlaps to non-trivial overlaps. But of course, all of this is a physical level of rigor. But at the mathematical level of rigor, there is a beautiful result concerning the 2D Gaussian free field by Bramson-Ding and Zaytouni, which I want to explain. So there are two ways, at least, to present the Gaussian free field in the discrete setting to simplify things here. First, it's just a Gaussian vector with this covariance function, where v and v prime have to be neighbors on z square. Okay, and I put a Dirichlet boundary condition here. And the other way is to say that the covariance is given by the Green's function. It's the exploitation of the time you spend at v prime starting at v for a random walk. And then after renormalization, again, the maximum will behave like log n minus the 3/4 of double log n plus a random variable, which is not quite explicit, but we know the tail. The tail is of the predicted type again, lambda exponential minus lambda, which is different from what it would be for independent random variables, like a Gumbel random tail would be just exponential minus 1. So if you want to cook a proof for this, you may want to mimic something that Bramson himself had done a couple decades before, which is to exhibit a branching structure. Where is the branching when you see that? It's not so clear. So the branching goes as follows. If you're interested in this value at one point, you see it as a value at the point minus the average on a small box around, plus this average that I just talked about minus the average on a bigger box, and so on. And that creates a hierarchy. And it's clear that depending on the distance between 2 points, the scales that I just talked about will be common or disjoint, especially because of the Markov property of the Gaussian free field. Like given the boundary, what happens in the box it only depends on the boundary, but not on what is outside of this boundary. So this is the idea, but there are obviously many important technical ingredients to come to that conclusion. But let me now come back to this Fyodorov-Hari-Keating conjecture on Zeta. Okay. Basically what they did is that they put the Riemann zeta function at the level of the extreme into the same class of models. And the conjecture that I stated before can be rephrased just like here, okay? And there are some amazing numerical data thanks to an algorithm by Gaith-Hari, who did something, I hope I will get my exponents right. He took capital T of order 10 to the 28, and that's where he looks at zeta along the critical axis. And he picks a number of random independent windows around that height and calculates the maximum at that height on a window of order 1. So that's really challenging, algorithmically speaking. and you get some data. So the data is a red curve, and that's after normalization by this log t, double log t to the 3/4. That's this MT, basically. That's the histogram of this MT, the red curve. The dotted curve is what would be predicted by the Fyodorov-Bouchot model, this explicit distribution involving the Bessel function that I mentioned. It's not quite the same, but it's the same shape, and it's very hard to do convincing numerics anyways, because when you start taking double or triple logs, even 10 to the 28 is far from sufficient. But still, it looks like it's on the good scale. For example, if you change this 3/4 into 1/4, there will be a much more substantial shift. Now, how did Fyodorov, Hari, and Keating come to that conjecture? Well, what they did is that they looked at the unitary matrices. And, oh, do I explain that? And what they did is that they take this integral, which is just a partition function for the unitary matrices, and there is a beta missing here, I'm sorry, determinant to the beta. And they calculate the moments of this based on some technology called the Fisher-Hardwick asymptotics in random matrix theory. They can calculate the small moments. They check that they match with the model of Fyodorov-Bouchot. And they argue with many different arguments that with this moment matching and maybe other arguments, maybe the distribution will match as well. So for random matrices, it's believed that the distributions will match. I will come back to that. Oh, sorry. Okay, this is where I wanted to go. So the results on the random matrix side are the best one is by Paquet and Zaitouni from last year, which proves that in fact the maximum for random matrix of this log determinant is log n minus 3/4 of double log n plus a random variable. And this random variable converges in distribution, so it's really the good scale. There's tightness and convergence in distribution. And I want to emphasize that even if UN is the most integrable random matrix ensemble, it has many symmetries, explicit formulas look simple, it's still quite difficult to achieve the distribution of the maximum. We don't know it. There was progress before, and what does this all rely on? We want to find a branching structure behind this log of this determinant. So let's formally just expand the log of 1 minus epsilon, treating the eigenvalues as an epsilon. And we obtain the sum of trace of u to the k over k exponential minus ik theta. Okay? And there is a beautiful result by Diaconis and Shashahani from the 80s, which states that these traces become Gaussian for fixed k when n goes to infinity. Independent Gaussian and variance of order k. So if you treat that as a square root k times a Gaussian, you actually come exactly to this Fyodorov-Bouchot model. So that's one thing which makes the connection. But another interesting thing is that we can see the branching here as well. So let me explain that a little bit. Basically, if you defined sk of theta to be the sum of this trace of u to the k over k exponential ik theta, but you're going to stop your sum at some level L, which corresponds to scales. So the variance is like the harmonic sum. It's this is k, this is 1 over k squared, so it's the sum of 1 over k. So what you really want is your k's to be smaller than exponential L. And we are going to consider L up to log n, the size of the matrix, because when L is greater than log n, we get n, and then these modes start entering the microscopic regime where very fine details of eigenvalues matter. So just look at this. And then with this normalization, you can justify that this else, for one given theta, you look at SL theta in terms of L. It's a bit like a random walk or a Brownian motion. That's true if these traces were really exactly independent and Gaussian. But now what if you take two different thetas? So that's for one theta 1, and you want to look at the trajectory for another theta. Okay. What will happen is that there will be a branching point for the trajectory of theta 2, and this branching occurs depending on the distance between theta 1 and theta 2, which will be minus the log of theta 1. What do I want exactly? If theta 1. That's right, minus the log of distance between theta 1 and theta 2. So basically what this writing suggests is that you can treat the maximum as a maximum of a collection of many, many random walks, which are indexed by these points theta. And there will be a branching really corresponding to a local-rated structure. And the reason why there is a branching at that scale, I forgot to mention that, of course, is because when theta 1 and theta 2 have some gap difference, as soon as k is greater than the inverse of this gap, these phases start entering into the picture and just randomize everything. Okay, so that's the picture for COE. And for Zeta, there's been a lot of work. So the conjecture was from about 2011, and there was a first result by Joseph Najundal under the Riemann hypothesis. Then with Sundararajan and Belus, we obtained that without the Riemann hypothesis. Adam Harper was the first one to get something of the right order in terms of second order for the upper bound. And what is known now is that this maximum really is of that side, of that size, both in terms of upper and lower bounds. So in particular, there is also the good tail. So if you do the histogram of the log so it's log t to the 3/4 over log t. You look at this random variable, make an histogram, we get a curve, and basically this curve really has a tail y exponential minus 2y on the right. This is one of the statements here. And on the left, it's not so clear what the tail is, but on the other hand, it's not supposed to be universal. But we know tightness. We know that there is no escape of mass on the left. Okay, so the second talk will be mostly about explaining this result. A classical question in talks about this topic is, okay, what about the real maximum now? Okay. Can we do something? The answer is essentially no, but I want to comment a little bit on it. Now we are not in a random world anymore. We really want to know what is the true gross order of the Riemann zeta function. So we know that it's subpolynomial if we believe in the Lindelof hypothesis. And there are two compelling conjectures. One will be that it grows like exponential, something slightly smaller than log t. And another one tells that it would be like an exponential of the square root of log t. The first conjecture would rely on the fact that there is some exponential tail in the individual values of zeta at random points. If you have a Gaussian tail, the maximum gets smaller and you get this 1/2. So somehow conjecture 1 may be consistent with what we have, because FHK, we have a y exponential minus 2y. We have an exponential tail there. But I want to explain that this is just a naive thing, and that's not quite what happens. In fact, if you try to cook an extended FHK conjecture, allowing y to depend on t and go very far in the tail, it's believed that it behaves once y gets larger than the square root of double log t, that it recovers Gaussianity in the tail. And actually, parts of this in some other models, and maybe even here, can be proved. But my point being that it's tempting to support conjecture 2. OK, so I'm not sure how I'm doing with the time, but this is my conclusion. I just hope I'm not early. OK. Yeah. So here is what is known and what is unknown now. So at the level of the extremes, we now know that the characteristic polynomials for random matrices and L functions, for some of them, really are on the universality class of log-correlated fields. The conjectures were obtained by physicists based on some calculations of moments. That's what they often do. And some assumptions on some scenarios of what happens for very small temperature. And to make a proof of this, we need to rely on Bramson's IDs and exhibit branching structures. And for Zeta, the key input will be a new multiscale analysis and some modifiers and twisted moments. I will come to that in the next talk. There are things which are unknown, many of them. There are some lecture notes which are on the table there. You can have a look, and there is a list of at least 10 open questions. One of them is convergence in distribution, both for Zeta and for random matrix. We don't know the exact distribution. What about the maximum for other L functions in similar settings? For Dirichlet L functions, everything we said works. But if you go to GLN for n at least 2, there is a problem that we don't know twisted moments of such L functions. And that's a key technical ingredient. Is there a similar picture when we do averages in families of L functions? We don't know yet. And a last question could be convergence to the Gaussian multiplicative chaos, meaning, if I go back to the very first slide, that this curve here is supposed to converge in measure to a random measure, which is so-called Gaussian multiplicative chaos, appearing in turbulence and quantum field theories. And this is not known. Okay. I will stop here. And so the next talk will be really diving more into the proof of this maximum for Zeta.
So questions or comments? I have a question about your conjecture. You say the distribution is not known. But even in the probabilistic case? Or?
So there is a conjecture about what it should be for random matrices. This XU supposedly converges in distribution to the same thing as a Fyodorov-Bouchot model. So this density. But we know it converges in distribution, but we don't know it converges to this density.
But now the other thing related is why Fyodorov, and they consider this.
Why they consider this?
Yeah.
Well, but, I mean, I think the motivation really is about having a simple model for replica symmetry breaking first, and the genealogy really is Derrida and Spohn, who did that on a tree structure, a direct tree structure. Then Carpentier and Ledussal in 2000 argued that it's much more general than just an actual tree. Any log-correlated field can exhibit this phenomenology. And then Fyodorov-Bouchot said, OK, there is this universal y exponential minus 2y tail and this RSB type of behavior. But is there at least one model for which we can actually calculate even the fluctuations in the partition function and so on, which is not known as far as I know for any model with RSB. So, that's obviously a very simple model, and there is an explicit formula.
Any other questions? Yes?
That's right. So the actual curve is non-universal, but the tail is universal. Now, the reason they are not, I can explain, is that it actually depends. For example, if you go to Zeta, imagine you take the log of Zeta and just close your eyes and assume it's correct to take the log of this infinite product in the critical strip. Now, if you change the small primes, if you decided that small primes are not what they are, that would change this distribution. But it will not change the tail. That's why.
Any other questions?
Yeah, so this is maybe for the next talk, but is the number theory ingredient in the proof of the equal moments, or is there more? Do you have to work harder?
Yes. We build on progress from the past couple decades, in particular what I call mollifiers and twisted moments. I will explain what this is. It's basically about calculating moments of the Riemann zeta function jointly with arbitrary Dirichlet polynomials. And there has been a lot of progress on this, in particular by my co-author Radziwill, on this question. And basically, we can calculate such things up to fourth moments. And it happens that for us, it's enough. 2 would not be enough, but 4 is enough. So we are very lucky that the number theory technology, which is just from a couple years ago, is actually exactly what we need.
All right, so maybe you have a lunch break, and we come back at 1:30. Thank you.